So anyway, we'll talk about gas transport and in particular LNG today. So there's something you can call the gas value chain. How you create value by transporting gas, and of course the origin of natural gas is plants millions and millions of years ago, which through time and pressure and heat typically would be converted from organic material to coal, to oil, and then gas. And of course, when we use coal, oil, or gas, we'll also produce CO2, which one might say, goes back into a cycle with the plants. But of course, the problem is that we produce much more CO2 than what goes into the natural cycle. So that's what we are worried about when it comes to climate. So there is a supply. There are some wells where one can harvest the natural gas. Then one can transport by pipelines. We can transport in long distances also by compressed natural gas, simply pressurize it. But typically, if you just pressurize at ambient temperature, it will still be a gas, but it can have, let's say, rather high density anyway. Then, of course, a much more used method is to liquefy it by cooling. That's what we call liquid natural gas. And then there are some methods that have been used for many years, and that is converting gas to liquid fuels. That's what we call GTL. And then there's gas to chemicals and gas by wire. That's an expression that is used by the industry, gas by wire. How can you send gas through a wire? Well, you convert it to electricity and then send it by wire, right? And there's one that is not listed here, and that is gas to solids. And that we'll also mention a little bit. Pardon me? Gas to liquids. You can, for instance, make diesel from natural gas, and we'll get a little bit into that. And they're different. You can make methanol from natural gas, plus many other things. It's a very valuable resource. So it's much more valuable than just using the heat energy. So here, and in one way, and it's listed first here because we haven't added much value, but if we take the gas as it is and burn it, for instance, for heating we need to heat our houses, then of course we utilize that gas directly. So that's what's called gas to flare. You may also think of having seen pictures from countries where they primarily produce oil, and you may see these towers with a big burning flame on top, and that's what's called flaring. And in many countries now that is not allowed because it's a real waste of energy, right? But of course, if there's no way of dealing with the gas at the site, where, let's say, the main production is oil, but when you pump up the oil, there's also gas coming up, and then some places they do flare it, they burn it. Also at offshore platforms you can see that they have a flare, but that is for safety reasons. If for some reason a too high pressure would build up in the processing system, for safety reasons, one would flare it, burn it, right? But it's a waste of energy. Also, gas to well, in some cases you have a production schedule for a well. You produce, let's say, you have both oil and gas in the reservoir. Very often, you'll find a layer of oil, and on top of it, there's a layer of gas. But the problem is if you and let's say this is the surface or the sea bottom. If you take out the gas first, then you lose the pressure that you need for the oil, right? So they would like to extract the oil first, but you may get gas coming up through the pipeline, and you are afraid of losing the pressure for the oil, and therefore the gas is separated out and then put back in the reservoir. But normally, after some years, one would like to produce the gas. So, in one way, it has a value to maintain the pressure in the reservoir. And that's particularly when you have both oil and gas. And then we have talked about pipelines. We have in particular talked about subsea pipelines, right? The deep pipelines, very complex systems and long distances now. Gas to tank, and that is, or gas to pressure vessel, I would say. It's what's called CNG. Sometimes they call it PNG, pressurized natural gas. But CNG is, I think, the industry term that is normally used. So CNG is at ambient temperature. It is at natural temperature, but it's compressed. So you can, of course, if you're going to transport it, you would like to transport as much as possible, and the amount you transport is dependent on how much pressure you have. So, for instance, you may want to transport natural gas by compressing it to 200 bars. And you need a lot of steel to do that, to have huge volumes of gas pressurized to 200 bars. Gas to liquids, liquid natural gas, and of course also the heavy components of natural gas, butane or propane. Gas to solids, natural gas hydrates. What's a hydrate? Hydro, water, right? So you have a method of mixing water and gas, and then you can get the gas out again by heating the hydrates. In nature, there are natural hydrates as well in the sea at very, very great depths of water, right? There are natural hydrates. There's a lot of interest these days in the natural hydrates. Maybe that could be a source for energy in the future. But we can also make it. We can make a hydrate. Gas to liquids, to methanol, I mentioned, and synthetic fuels, artificially made, so to speak, fuels. Gas to wire, I mentioned. Gas to hydrogen. You can make hydrogen from natural gas. Gas to plastics. different plastic products, fertilizers, or even protein that we can eat. So with modern chemistry, you can sort of split the molecules, take them apart, and then put them into different new configurations. Of course, there's an energy part of that equation, and it's not always very smart to do so, but you have a lot of flexibility with modern chemistry in making new things. And of course, carbon, oxygen, and hydrogen are major components in these products. So kind of putting these atoms together in various ways, we can make different products. So for instance, if you have a natural gas coming in from a well, you can make methanol, you can make hydrogen, you can make synthetic gas and get some CO2 that you should take care of. You can get ammonia, also called azane, NH3. And then we're talking about this link into fertilizers, right? Nitrogen compounds. Yeah. So you can, I don't understand this diagram why they put electricity here after hydrogen, because I don't think you'll make hydrogen and then electricity. I think you'd rather use a gas turbine and the natural gas going into the gas turbine, and the gas turbine drives an electric generator. But as you see, chemistry there are so many possibilities. So let's just take the gas to liquids. What's the advantage by transforming a gas into a liquid? It's easy to transport, right? You just put it in a bucket. It's no pressure, no cooling, and that's what we call fuels. So we would like to have it in liquid form. Unfortunately, to get it into the liquid form, we need to add energy. But for instance, during the Second World War, Germany had a lack of fuel for their operations, and they made a lot of diesel and fuel for their war machinery, starting with coal, because Germany had a lot of coal but didn't have any oil or gas. But one can use coal, or one can use gas. And and natural gas very often is about 80% methane, right? You know what methane is? It's a high hydrogen fuel. It's a low carbon fuel, right? CH4. Okay? So you kind of you have a natural gas where you have different chemical components in the natural gas, and then you sort out the heavy parts, like more like butane and propane and that sort of thing, and the methane, the lightest component. You get into this gas process where you have you get oxygen from air, for instance, by what do you call it? Electrolysis, and then you do a synthesis with and get hydrogen and carbon oxide, and what's called the Fischer-Tropsch process, which is a German process from the 1920s. You can make liquid hydrocarbons, diesel, naphtha, paraffin. And that is one source. But as I said, you need to add energy. And normally, it's maybe better to use the natural gas in other ways, but this is certainly a possibility. Let's think in the future, for instance, if we ran out of oil, but we still had gas. Well, we would like to have fuel for our cars and other purposes. Then we could make diesel this way. And it is being done. But particularly in situations of crisis. Okay, so that's some of the background. Now we would like to talk about marine transportation. And we already have covered subsea pipelines, right? Then we have compressed natural gas, we have liquid natural gas, we have gas to liquids. And distance and cost per unit is drawn here, and you see if the market distance is very long, then there are certain, it's very, I'm just wondering now, this axis, the cost of CNG transport. Okay, well, it's more the investment cost here that goes here. So if the investment cost is rather high, and then of course also the added cost of distance, if that is also high, for instance, a pipeline is typically proportional to the distance you want to transport. So the pipeline becomes too expensive if the distance to the market is too long. Whereas LNG, the cost you put into the LNG is primarily in the chemical processing, the cooling. It doesn't really matter how far that ship is going, because the ship transportation is very cheap, right? But there is a basic investment which is rather costly, so it doesn't make sense to do a LNG transformation if the distance is short. It's only when the distance is long, LNG is being competitive. But if you have a rather short distance, an alternative to pipeline could also be to compress the gas, because compressing is not quite as expensive as liquefying the gas. But the transport per length is more expensive with CNG. And also when you think about the energy loss, pipelines, well, of course, the cost of the energy cost of transporting in pipeline has to do with the friction in the pipeline, right? You have to add pressure, and how much pressure you have to add to get the gas through, and also the speed depends on the pressure difference at the inflow and the outflow point. So you need energy to overcome the resistance, the friction in the tube, right? So if you have a very long pipeline, then of course the loss will be higher than for a short pipeline. With CNG, the pressurization also implies you have to add energy, right? And then you can say that about 5 to 8% of the energy content in the gas is lost by having to add this energy. And for LNG, the cooling is even more expensive. Then the cost is about 15% in terms of energy. You have to use more energy to cool it than you have to pressurize. And gas to liquids, that is very demanding when it comes to these chemical processes where you may have to have electrolysis and you may have to add additional energy. So one is talking about 20, 30, 40%. So that is the process cost in terms of energy. So we have gas production at the well, liquefaction, we have shipping, we have, when you come for instance with the LNG ship, of course you have to heat up the gas, the liquid gas, in order to put it into pipelines and transport it to the consumer or to the industry that's going to use the gas. Okay, normally that energy is taken from the sea, so it's not a very costly energy, right? So typically these regasification terminals, and you have several of them in Korea, they take the energy from the sea that is needed to heat up the gas. But do you see some strange things at this picture? Something that is not really right. I'll start here. This is an oil pump, isn't it? Right? So you have to be a little bit critical. I don't think this is a gas pipeline from a regasification terminal either. It looks like from a certain field. But anyway. I won't go too much into this phase diagram for natural gas, but you can go between liquid and gas to gas, and of course a pure liquid. And if you have atmospheric pressure, then you have to cool it a lot to minus 162 degrees or less, or colder, in order to make it liquid. So 162, 163, in that range is where the methane, which is the lightest component of natural gas, becomes a liquid, right? And when the gas is at minus 162, it's a liquid at the boiling point, right? It's really a boiling point. We think of water, right? When it goes from water to steam, that's at the boiling point. But liquid natural gas is at the boiling point at minus 162. And you have this shifting between the liquid form and the gas form is very close. And of course, in a LNG tank, you have both a liquid, and above the liquid, you have an area where you have the gas form of the natural gas. But that gas, which is also around minus 162, is a very heavy gas. Very heavy, relatively speaking. So when you get the gas from it says transportation here, I would say the pipeline from the well, then you remove the heavy components, you remove CO2 that often comes along, you remove water, And you remove also other compounds that may come along, like mercury, certainly, and sulfur, hydrogen sulfur components. You don't like to get those into the transportation system. So that kind of cleaning has to be done for the gas before it's refrigerated and thereby becomes a liquid, and you need a storage, and then you get it onto the ship and transport it to where you want to go. And you see, the density of LNG is less than half the weight of water, right? So it's really a light cargo. So what you would like to have on an LNG ship is huge tanks. You don't want to waste space because your cargo is light, right? So tank efficiency is important. Okay? So if you compare with diesel, you see it's much lighter. And also the caloric value, the burning value of LNG, when it comes to how much energy do you have per cubic meter, and that is, how much energy do you transport on a 200 cubic meter storage on the ship? Well, it's less energy if you have LNG than compared with diesel or oil, other types of fuel, right? But anyway, gas transport is very important, and gas is a much cleaner fuel than, for instance, crude oil, right? So there are many reasons for doing exactly that. These are just a repetition about the market, how it's now developing around the Pacific Basin, the LNG demand, and then the Atlantic Basin, and also a lot of growth there. But as I mentioned, there is one uncertainty factor these days, and that is what's called the shale gas, right? What the Americans are doing with the shale gas, which they have a lot of, which is not a really good source because it's the process of getting the shale gas out of the ground is polluting. But for strategic reasons, and that is the United States' energy dependence from importing energy, right? That is a problem for that country. That's why they're pushing this shale gas. And the market is a little bit nervous about this development. But anyway, the gas market is certainly increasing, and increasing rather rapidly. And also this one you saw, we have a lot of old LNG ships that have to be replaced. So these are ships more than 30 years old. And it's not difficult to make these statistics, right? Because these ships were built 30 years ago. One knows exactly how many ships that is. Of course, what is a little bit uncertain is if these older ships will be phased out, when they are 30 years. They are probably a little bit less efficient in many ways, but the investment cost of a new LNG ship is very high. Depending on the size, we could talk about $500 million. They can be very expensive, these LNG ships. So it's a matter of economy and as well as safety. And also economy of scale we talked about, and now the focus is on the big stuff, the large tanks, and how can they be made. So we'll spend some time now on talking about the main types of tanks for LNG. And the LNG history goes back to the 60s, I think at the late 50s. So it's pretty long history in one way. But the first tanks that were built on a large scale, those were the spherical tanks, and a design by Moss Marine in Norway. So about 50% of all the LNG ships in the world are with these types of spherical tanks, and we'll look into how they are designed. Then there is a Japanese, I won't pronounce it, but IHI. So they have a self-supporting prismatic tank, and we'll talk about different tank shapes. A prismatic tank, it's like a box tank. And a box is more efficient than a sphere when it comes to utilizing volume, right? When you put spheres next to each other, you have a lot of space in between. Whereas if you have a box type structure, you can pack things much better together. But this hasn't been a very great success. So only 2 vessels have been built by this system, whereas here we are talking about dozens, probably more than 100. And here you have 2 types of membrane type tanks. One is called Technigas Mark III. Now it's only referred to as Mark III. And the other one is gas transport, which is using another type of membrane tank, where the primary barrier is Invar, which is a metal which doesn't have any thermal expansion and contraction. Because you understand that temperature is a very difficult part of the design. When you cool something down nearly 200 degrees from room temperature to minus 160 something, then of course you have a huge contraction, thermal contraction. And that is a real design challenge. And what has happened? Well, there's a company called Technigas and Gas Transport combined, GTT, that is controlling all this technology. Of course, many of the old patents have gone beyond their protection time, so they are open. But there's a lot of technology in addition to what is in the patents. So this company is more or less controlling all the LNG tank systems. And of course, I'm sure the Korean yards, as well as many other yards, are not very happy with this monopoly type situation. And I know Korean shipbuilding industry has been very much interested in developing Korean concept for LNG. Right? So far, it has not happened, but I'm sure it can happen. And I think certainly there are alternatives that really could be competitive today to these existing systems. So this is quite an important topic. And for instance, GTT, I've heard about what kind of fees they are taking for consulting. Fantastic prices they can charge for their technology. For one ship, the license may be in the order of $5 to $10 million just for getting access to the technology. So you can understand that the Korean shipyards are not too happy to have to pay so much for this technology. And additionally, possibly also consulting fees to the engineers from GTT. So how are these systems made? So we have the spherical tank, and of course you have to carry this spherical tank, and that is done with what they call a skirt here. So you have a cylindrical shell that is supporting a spherical shell, and that you do along the periphery because you don't want to introduce bending in the spherical shell. Understand? So you have a sphere, and the best way of supporting it is to extend the vertical sides, and then of course you have some sort of integration with the ship down here. But when the tank contracts, because it's getting cold, right? Then of course this has to deform. So you do get some thermal stresses in that structure. So these tanks have been built of two types of material. One is aluminum. Aluminum is a very good material for low temperature because it doesn't get brittle. Aluminum gets tough when it gets colder, whereas steel, and I'm not sure how much you know about material technology for steel, but you know there's a transition temperature when you get to minus 30, 40 degrees. Carbon steel gets very brittle. And brittleness is something you really fear because that means you can have brittle fracture, right? So you cannot use regular carbon steel, but one can use, for instance, a nickel steel, which is a modified steel, but you have to add a lot of nickel, 9%. And by doing that, you get a steel that has good properties also for low temperatures. And you can weld it. Welding is, of course, very important when you're going to build a large structure. You have to put together pieces, and that's how you can make this tank. Very large tanks. And then you insulate the tank on the outside, and you have what is called a drip pan. If there is a crack in the tank, the liquid will flow down here and be collected in a drip pan here. But of course, by all means, you don't want that to happen. But there are gas detection systems that will discover if you have a crack and a leak in the tank. Okay? And the design criterion is leak before failure. What does that mean? Well, if so should happen that you have a crack in the tank, that crack should not become brittle and you have a brittle failure, because then of course you'll have a catastrophe if the whole tank breaks down. But if the crack just opens and lets out a little bit of gas, you'll detect that there's a defect or a small crack in the structure, and then you can. The rule is that the ship should be able to go to shore and unload the cargo before the crack becomes unstable. You understand this? So leaking, of course, should not happen, but if it happens, the material has to be so tough that with the crack and with the liquid coming out, it still should not become a brittle fracture failure, right? And then there are these two other membrane tanks, which are more prismatic. They typically have two barriers, a primary barrier and a secondary barrier. And for the GT concept, the primary barrier is 36% nickel steel, which is Invar. It's a very expensive material. And in the case of Technigas, it's stainless steel, but that's normally also 9% nickel steel. And that is a corrugated membrane. We'll look further into that. Why it has to be corrugated, and that has to do with the contraction, of course. So important things to consider. I already mentioned this, structural integrity of the tanks, the failure mechanisms. You should not have brittle failure. You should not have a large crack opening. And if something is wrong, you have a strategy to ensure that you don't have a total failure before you can get to shore and have repairs. Then you have to think about the interaction between the tank itself and the ship. And of course the ship is a flexible structure. If you think of a ship in the storm, you know, it's a beam that bends and twists and all that. So you have to think about how is the tank connected to the ship. Well, of course the principle for a spherical tank is very much different than a membrane tank, where it's the inside of the cargo space which is cladded with this membrane and the insulation. So, and of course these days it's floating LNG terminals is also becoming an area where we want to have large tanks, not only on ships, we want to have large tanks on terminals. So leak detection, inspection and repair. And then there's something which also has to do with modern technology. And modern technology where we have floating terminals and ships coming to the terminal out at sea. And of course, out at sea there is waves and wind and the ship is moving. And inside these tanks, the liquid may be going back and forth, and that's what's called slushing, right? And if the tank is not very strong, this kind of motion of the tank can lead to damage. Not so much in this type of tank, but certainly for a membrane tank. And there are very strict regulations for membrane tanks. These tanks either have to be full or they have to be empty. You understand? Because if there is, let's say, a part filling of the tank, you'll have this problem with the liquid going back and forth and damaging the tank. And there have been many cases where membrane tanks have been damaged on completely new ships. Very recently, some built in Korea. So, and that is of course terribly, terribly expensive if you have that sort of damage. So that's the weakness with the membrane tanks. That is, they cannot normally sustain partial filling. And that's what we would like to have in many cases where the ships interact with terminals, either terminals that liquefy natural gas or terminals that make it into gas again, the regasification. They are more and more becoming offshore terminals, right? And that's why one will have the problem of the ship at sea with maybe partial filling of the tanks. Fabrication schedule. How long time does it take to build such a ship. You know, the capital cost, if it's a ship that costs many $100 million, what do you think it costs per day to have it without getting into operation? It's really scary if you start looking at that. And of course, the schedule, when you first start pouring money into building a ship, it's very important that you do that very quickly. And of course, that is a competitive advantage in many cases for Korea, because you are very efficient at manufacturing, right? So it's the cost and operational expenses, and also for the entire system, the environmental performance, which is becoming more and more important. So it's volatile organic compounds, volatile fumes coming out, but nowadays one is much more efficient and have systems for taking care of the vapor. Remember that liquid natural gas is boiling at the boiling point, and there's no active cooling system of the tanks themselves. The cooling is actually from vaporization of the from fluid to gas. That's how the cooling takes place. And of course, when it goes from fluid to gas, it expands, and you cannot have this pressure building up inside the tank. So you have to release that out. Well, nowadays, those fumes are cooled and put back into the tank after being condensed again. So you actually use energy to make it cold again, right? Or in some cases, one can use the vaporized LNG to as a part of the fuel for the ship. For instance, if you have a combined engine that can burn both LNG and diesel. Okay? But of course, you have to have some kind of agreement with the dealer, owner of the cargo. I mean, the ship owner cannot just steal the cargo. This has to be a part of the equation, right? So these Moss tanks, and I'm sure you've seen many pictures, they have typically 4 to 7 spherical tanks. I would say 7 is very unusual. 4 and 5 is the most common. And under here you have a lot of insulation, right? But you see these, in one way, these spherical tanks don't fit very well into ship hull. So, and the way the fees are decided when you go through the Suez Canal, this is an additional cost by having the spherical tanks. They are much more, have to pay much higher fees for going through the Suez Canal than the membrane tanks, and that's because of the volume above the sea. So here you see another picture, right? And of course the hull is more narrow here, so here's a smaller tank, etc. And recently one has been studying a lot of variations where the tanks have been kind of extended in vertical direction to have more volume on board, right? Because the cargo is light. So the spheres are very inefficient when it comes to volume utilization, and the cylinders are better, but they are not perfect. So prismatic tanks are more efficient in terms of volume. Oops. Okay, let's just do this one. Some of you are taking the finite element course. This is, I'm just showing you an example of a real problem. I'm not sure how many real problems you see in that course, but this is an example of a finite element analysis of a LNG ship with this Moss spherical tank concept. So, and when you start looking more into detail, you can see that a finite element model is built from what is often referred to as substructures or super elements, that is, elements that are consisting of many other elements, and you can build parts on different levels by putting together parts of a lower order, right? So, for instance, you have a detail here, very important one, having to do with the support of the sphere, and you have a very detailed model here. You have the lower part, you have the upper part of the shell. Here's even more fine detail, and where you use very, very, very small elements to get the stress concentration where you have the support, right? The elements may be millimeters. And then, on the other hand, you have a ship that is 200-300 meters long. So you see the complexity of this. You want to do detailed analysis at the local level because you're interested in stress concentrations and fracture. And at the same time, you want to look at the interaction between the ship and the tanks, right? So it's a very, very complex analysis, but you can do a part solution and a condensation where you put together these elements, so you don't have to solve everything at the same time. But anyway, if you look at the number of finite elements in a model like this, we are talking about hundreds of thousands and millions of degrees of freedom. But this is a standard type of analysis that can be done today with large computers, but still, it's a standard analysis. So we have finished the spherical tanks. Now we are getting more into the membrane tanks. Some of the, I have quite a few slides, and I'm not going to go through all the slides, but I would like you, since I have it, to give you some more background information. So some of these figures you can look at yourself and see if there's information there that would interest you. I must say these LNG ships are pretty impressive, and here you see a membrane tank, and you see a person here. It's enormous, right? And still they want to build bigger tanks. But you can also understand that if you have a partial filling of fluid here, that is going to go back and forth, sloshing inside the ship. So that is a problem. And here in the Mark III system, you see these corrugated panels, and the corrugation typically is like this. And of course, when the material contracts due to cooling, you have the possibility of this stretching here, right? Without getting too high bending stresses. But there are certainly problems with such tanks. One is that the metal in principle can crack. Another thing is the problems with all the welds. And you'll see pretty soon that for the Mark III, these things have to be um, welded together in these corrugated panels. Here is a large LNG ship. You see some typical sizes of these tanks. Total height 26 meters, width 44 meters. And of course these tanks don't go all the way out to the side. And why is that? Well, you have to think about, if you have a collision, you have to have maybe 4 meters, 5 meters as a safety zone, because you don't want that other ship to penetrate and open up the membrane tank on the inside, and that tank is not very strong, it's just a very thin material. So, and the cargo is light, and someone would like to have larger volumes, and these are some of the recent proposals to at least get a little bit more space on board by extending the tank like this. But of course you also build up higher pressures inside the tank, right? And I would think that one other consequence is that you have to pay higher fees in the Suez Canal. Here are some of the figures that you can look at yourself, but you see this is the ship, and of course the ship, you don't want the cold gas by any means to get as far as to the ship structure, because that is built of steel that will get very, very, very brittle if it's cooled down to minus 160 something degrees, right? So you have insulation, and you have one barrier here. This is the secondary barrier. Then you have insulation, and then you have this corrugated nickel steel on the inside of that. But there are so many pieces, there are so many special pieces. These are really quite complicated. So even though it looks like a smooth, fine, not a smooth, but let's say a uniform type of surface, corrugated surface, there are lots of details having to do with corners and different angles and parts that have to be put together to make such a tank. And they are very expensive. So some of the details here with the secondary membrane and the corrugated top layer, right? It has to be corrugated in both directions because, of course, you have contraction in both directions. More details: the thermal insulation, glass fiber reinforced insulation, and the what's called a triplex membrane, which is the secondary. And in between here you have gas detection systems. If you have a leak, the idea is that it's going to be detected before really getting to the second, through the second membrane, because if that happens, it's bad news. Yeah, some more detailing. How it's attached to the ship structure, bolted. So there's a lot of handwork, so to speak, here. More details about the membrane. Welding. Lots of welding. Look at this. This is one of the corners. You see these welds? In rather critical areas. So, I'm sure the people who do that welding has to do a lot of training. And of course, after the tank has been made, it has to be tested. Normally by applying some overpressure between the internal and the... Is it overpressure or under pressure? Maybe it's under pressure. I'm not sure. But anyway, there's some pressure tests to see if it's leaking or not. This is the IHI tank, right? It's that has only a single barrier, and it's like almost any other ship tank, quite much welding work to do here, and rather heavy. Supported on blocks, and of course this contracts too. So it's a self-supporting, or it is really a separate tank from the ship structure. But of course the bottom of the ship structure will also move somewhat, so that kind of deformation has to be allowed for. And there are some ships that have combined tank systems that can handle different types of gases. Ice-breaking LNG ships. See this one? Ice-breaking bow. We'll get more into this principle of ice-breaking later on, but it presses down the ice, fractures it, and pushes the ice to the sides. So in principle, this one can go through 1.5 meter thick ice. So not a very, very large LNG tanker, but still, no, 70,000 tons. And of course, some of these new gas fields are in Arctic areas. So is this safe? There have been a good deal of accidents, grounding, collisions, spills, engine fires, not major consequences. LNG is lighter than water, and natural gas is lighter than air. It will tend to evaporate into a cloud. So methane gas is lighter than air, so it will go up. But if it comes out as a liquid, that liquid will spread on the surface of the water, right? But it's not that easy to ignite. You see, you have to have the right mix of air and natural gas in order to be able to ignite it. So that's between 5 and 15 volume percent. But it's dangerous to people, of course. You'll suffocate if you only have breathing methane, and it's terribly cold. And for the structure, I talked about the temperature problem and the brittle behavior at low temperatures. A ship of this type could be a target for a terrorist attack. One saying is that a LNG ship is like a small atom bomb. Well, it's not that easy to make it blow up, fortunately. But we don't really know what will happen. But there are some studies of the safety and security relating to LNG ships, and there's a reference. Land tanks, I'm not going to talk about land tanks, but they are, of course, important in connection with terminals, and in principle you could build such a tank also on a floating structure like a floating terminal, but the land type of tanks are normally very heavy. They are concrete outer shells, and then they have an inner tank which is made of nickel steel, 9%. The same as you see on the ships. So in Korea, of course, there are no liquefying terminals because you don't have any source of natural gas, but you have the regasification terminals. So there are some of them and some very large ones. I think at Incheon there is more than 20 different LNG tanks. Different sizes. Big. Big stuff. Yeah. So, as you see from these pictures, you have some places these LNG ships. Here's one, as a matter of fact, with 6 spherical tanks, and here's one with 5, going up rivers. In Boston, you know, the big city of Boston on the east coast of the United States, they had the LNG ships going into the busy harbor. I think they have built the offshore terminal now, but that was certainly a safety problem. So, again, the kind of technology we are interested in, which is, you know, the offshore floating plants, regasification plants, etc. That's the kind of technology that is coming more and more and becoming very crucial, this technology. So a floating LNG plant can be moved to almost any location. You know, it typically can look like a process ship. No pipelines to shore needed. Can serve smaller fields. Smaller fields that produce maybe 5 to 10 years. And when it's empty, you can move the ship to another place, right? So the investment cost can be shared by several fields, and it's less controversial than onshore plants. And that is particularly in the United States. There's been a lot of resistance against LNG terminals. For instance, the west coast of the United States needs a lot of gas, but they don't want the terminals. And they want rather to build terminals in Mexico and send it up to the United States. But this is what it may look like. You have a LNG liquefaction plant, right? So there's a gas well down here, a resource offshore. There you have some tanks on board, and then this LNG ship comes in and gets filled with a liquid natural gas. And here you see spherical tanks where the problem with partial filling is not significant, because the tank itself is much more robust, and sloshing is less of a problem in a tank like that, because the local buildup of pressures is much smaller. So different types of tanks could be used for such liquefaction terminals. Here you see some ideas. And of course, prismatic tanks has the advantage of being better integrated into the structure. You know, the prismatic, the box-like form. And here's one concept that ExxonMobil worked on for many years and invested a lot of money into, and finally implemented that in a offshore terminal in Italy in the Adriatic Sea, not far from Venice. And it was built in Spain. You see the size of it? Designed by Aker Solutions. It has 2 tanks of 125,000 cubic meters. And it's the ExxonMobil tank concept. Designed by Skanska, a Swedish company, and fabricated by HHI. So these tanks were transported to Europe and installed in this concrete floater that was floated to location and set down on the sea bottom. Okay. So the water depth at that location was sufficient for very big ships to come into the terminal. See the transport of the tanks, special ship, so enormous. But this in one way doesn't look very good, this interior of that tank. So I don't know how many of these will be built in the future, but for this particular case, Exxon decided to use its own tank concept. Yeah, here's another illustration of what such a floating LNG terminal could look like, right? There is a interesting book called Natural Gas by Sea. It's about the history of LNG transport. And it's written by a person by the name Roger Fox. I think he is Dutch, from Netherlands. And one quote from this book that was written at late 90s, it's difficult to see how any radically new containment system now can succeed. Quite apart from the very considerable time and cost to develop, it must, as always, hold a potential capital cost to develop, hold out the potential cost to develop. It must, as always, hold a potential cost savings of well over 20% to have any chance at all. This possibility now seems so remote as to be virtually non-existent. Well, I think he was wrong. He had been working in that field and thought, well, this is as far as technology will come, what he has been involved in. But of course, there are new ideas coming up, and certainly a very great market pressure, market push to develop new technology, which is price-wise competitive. But I've been involved in projects like this, and what is said here, in order for a new concept to be interesting, it should have a cost saving of at least 20%. So it has to be smart. It has to be smart technology in order to be able to succeed. So I'll give you some examples of LNG innovations. And these are examples that are to a large extent based on my ideas and projects that I have been involved in. So I have some background for this. So, but the new market demands large vessels, efficient in relation to fees, so that is preferably spherical, preferably prismatic, offloading at offshore terminals, partial filling, should be able to handle that. And for offshore terminals, if you install the tanks there, they should have a life of at least 40 years without maintenance. So that is the challenge today, to come up with concepts that can break through the difficulties of barriers in relation to existing theory and existing technology. Yeah. And sloshing is certainly a very important part of this. But the current technology has certainly weaknesses. There are lots of codes and regulations, and these regulations were established nearly 20 years ago. And they kind of are focused on technology that was existing 20 years ago and probably should have been written in a different way today. But here you see, for instance, for membrane tanks, they should have a complete secondary barrier. And then there are independent tanks that are not relying on the ship structure, but they are separate tanks that standing inside the ship structure, right? And there's a type A and a type B and a type C. So a type A has a complete secondary barrier, a type B has a partial secondary barrier, and type C has no secondary barrier. And when you talk to oil and gas companies today, they say any new tank they want to get involved in, and I've been involved with BP and Shell in this connection, and Statoil, they say we want a type A. We want a independent tank that has two barriers. So how does one make that? That's the big question. Something strange happened with the consistency of formats here, but anyway, we had what is called a joint industry project. There were 3 big oil companies involved: Statoil, BP, and Shell, and there were 2 shipping companies involved, and Aker Yards and Aker Solutions and DNV. So we had a series of concepts that we proposed: a sandwich tank, a semi-cylindrical tank, double barrier, panel tank, and what we call the cell tank, and then an integral tank that was really not considered too much. But anyway, we did quite extensive studies of this, and we did patenting of these 4 first ones. And we did, through 1 year study, various alternatives. And in the end, here you see the idea of using lightweight concrete as insulation material, and I have 2 barriers. It's like a sandwich. You have a steel membrane on the inside. You have the core material of lightweight concrete, and then a steel barrier on the outside. So you have a lot of structural strength and integrity. So the insulation material in this case is a part of the structure. So that was one of the alternatives. And you see it's almost prismatic tank. But the one we ended up with after 1 year was the one that was called a cell tank. It was given the name ADBT. I don't know exactly why, but aluminum double barrier tank. So I'll show you some pictures of it, but it's a complete double barrier and made of aluminum. And aluminum is a very good material for low temperatures. And the walls are made of beams that are welded together. And inside there are a structural system that has 2 purposes. One is to hold the walls in place, and the other one is to prevent sloshing. So this is the particular grade of aluminum used for this tank. a type of aluminum which is strong and weldable and suitable for low temperatures. So the wall elements are extruded H profiles of aluminum beams, and these are welded together, so you get a double wall by stacking these on top of each other. And inside you have a cross-linking beams which hold the walls in place, and of course also have a strength when it comes to the tank moving in the sea, right? And when you design the tank for a ship, you have to design it to be able to withstand 30 degrees roll. And that is pretty serious loading condition. When the tank is on the ship, and this is 30 degrees. Then of course the force component in this direction is 50% of the weight of the tank. Pretty serious stuff. And also the tie-in of these internal beams, very important detail in order to avoid fatigue and cracking. I think we've found an excellent solution for that. Here you see another picture. And this method of friction stir welding is maybe not so well known in the shipping industry, but it is being used in construction industry for other purposes, and I think it's also used for car decks inside ships. So you see two aluminum plates put next to each other, and then there is almost like a drill on the surface that's rotating, and it has a pin that goes in this crack between the two plates. And by rotating and having a pressure on it, this you see the result. You know, the material melts, but then of course hardens again, and the surface is completely smooth. And there's no welding material added. It's only the material of the plates that melts and fuse together. So here you can see where some of these beams have been welded together into a panel. And also modular construction of the entire tank. Sloshing analysis, and of course, because of these internal beams that are linked together like this, there's very little major sloshing, just, let's say, local sloshing in these chambers. So, thereby one can avoid building up very high sloshing dynamic pressures on the tank walls. But anyway, these tank walls are very sturdy, very strong, and can take quite a bit of pressure. But in reality, the sloshing problem is virtually eliminated. And Aker did some analysis of different types of ships, and the concept is completely scalable. You know, you can make the tank as large as you want because it consists of cells that are equal. So it just extended. It's more a matter of how practical it is to have a very large tank. But since it's an independent tank, you know, you can have it, for instance, inside a ship for ice conditions where the ship hull may be deforming quite a bit because it's a separate structure. You can have loading, unloading in severe weather conditions, and by having several tanks, and you can do partial delivery in one place, and it doesn't matter that the tanks are only partially filled when you go a stretch at sea. And also what they found out about this concept is that the production time will be much faster because you have a complete parallel production of the tanks and the ship, and you can push the tanks inside the ship, and thereby, as I said, have a parallel production of the tank and the ship. Whereas if you think of a membrane tank, you have to build that membrane tank after you have built the ship. And of course that takes several months to do. So with the capital cost, this is a major cost saving. So the advantage is scalable, independent, box-like, all levels of filling, cheaper in production, shorter construction time, easier to repair, it's lighter, and strong in collisions, and it is approved as a tank type A, double barrier independent tank. And this was a little bit back and forth because Aker Yards was sold to a large extent to STX, but this part of the technology was kept outside that deal, and there were some Russian companies getting involved in this, and it turned out they during development they had some economical problems and their whole project collapsed. But Aker Solutions has now taken over the technology and they are developing this. And this is one of the tanks, smaller tanks, for startup they want to build a smaller tank. So that will be used along the Norwegian coast now to supply LNG to coastal vessels. And they are also planning much larger tanks, but they're going step by step. So they're saying they will be able to build single tanks of up to 150,000 cubic meters. So that will be interesting to see, and for me, it was my original idea to see if this really is going to happen. So I would think this kind of technology will be on license from Aker Solutions, and they are building more like terminals. They are not building ships, so there could be opportunities there, I would think. So that was the last slide. I know there are other possibilities too for LNG tanks. Like I worked on one concept with a box type prefabricated box type which is more integrated with the ship hull, like a membrane tank. I think that concept could also be something for the future, but it's a different concept from this independent tank. So you have to notice the difference between an integral tank, which is sticking together with the external structure, and one which is independent and standing all by itself. Okay.